Okay, this is going to be chapter 21, Global Climate Change. So, to put this into perspective, we're going to very briefly cram in about 1/4 of a course of physical geography dealing with one of the four spheres of the Earth: the atmosphere, hydrosphere, geosphere, and biosphere. We're going to deal with the atmosphere. So, to put this into perspective, what we're talking about are the changes and effects in the atmosphere, both natural and man-made. So, let's get a couple of terms out of the way. Weather basically describes what the atmosphere is doing over the short period of time. Climate is the average weather pattern in an area over a long period of time, typically taken to be about a 30-year average. So when you watch the news at night, assuming you watch the news, and you see the weather forecast, and they say that the average high is X for a given day, well, that's the average high for the last 30 years for that date. Generally speaking, the average is a running average. So they take the past 30 years worth of data and average it. So when they put today's weather numbers in, they will drop the one from 31 years ago out of the system. One way someone else has put it is climate is what you expect, weather is what you get. Now, we have a lot of concerns over climate change in that we have become, as a species, less adaptable and more dependent on consistency in the climate of the Earth. So, first and foremost, to really kind of start this out, we need to understand the atmosphere. So, what is the atmosphere made of? How is it structured? By composition, the atmosphere is a number of different gases. Now, we're probably on something like the 6th or 7th different atmosphere that the Earth has had since it formed. We're not going to go through all of those atmospheres, but suffice it to say, when the first atmosphere formed on the Earth, it was not one that was conducive to life as we know it today. It was high carbon dioxide, probably high nitrogen, no oxygen to speak of, probably some other trace gases that or gases that are traced today that were more prevalent back then. But basically today, the composition of the atmosphere is 78.08% nitrogen in the form of N2, so a molecule of nitrogen, two nitrogen atoms joined together. It's about 20.95% oxygen, again in the form of O2. And then it's about 0.93% argon, 0.0397% carbon dioxide, and then we go down below that with neon, helium, methane, nitrous oxide, and other gases. So the atmosphere is made up mostly of nitrogen and oxygen with a trace amount of carbon dioxide and a even smaller trace amount of other gases, a minor amount of argon and a trace amount of carbon dioxide. In terms of the structure of the atmosphere has different layers in it. We can look at them in a couple of different ways. One way is to look at in terms of the nature of the gases and how they're arranged. In that, the atmosphere has basically two layers, the homosphere and the hydrosphere. Basically, one is where the gases, the bottom layer, the hydrosphere, is where the gases are all mixed together. They're jumbled. The homosphere, the gases are all in layers, and they're actually in layers by density. So the heaviest gases are on the bottom layer, and they go into layers lighter. Another way we can look at it is in terms of how the temperature varies through the atmosphere. When we look at it that way, we have four layers, and these are very important layers for us. The bottommost layer is the troposphere. This is a layer where temperature decreases with elevation until you get down to about minus 60 degrees centigrade or minus 75 degrees Fahrenheit. at an altitude somewhere in the neighborhood of about 10 kilometers. Above this, from 10 kilometers to about 46, 47 kilometers is the stratosphere. Above that to about 85 kilometers is the mesosphere. And then above that is the thermosphere. And what you see is interesting. I'll hold it up in the book here, page, if you're interested, 509. You can see the way that the temperature changes in the atmosphere. Lowering, there's a pause, and then it increases, decreases, and increases again. Now, as we go up, the density of the atmosphere is greatly decreasing. When you're at 10 kilometers above the Earth's surface, about something like 50% of the Earth's atmosphere is below you, even though the atmosphere goes out to about 120 kilometers. At around 25 or 30 kilometers, somewhere in that ballpark, I don't have the number exactly in my head, you're at 90% of the atmosphere is below you. May even be a number lower than that. I might be misremembering. It's been about 2 years since I taught my physical geography class, so I haven't looked at my notes recently. Now, what is important about this, though, is the composition of the Earth's atmosphere plays a role in the climate, but it also is a role that is dominated in part by the sun. The sun brings in energy to the Earth's surface, and depending on how the Earth is oriented in space during the time of year, the amount of energy per square unit area, or what we call the insolation, incoming solar radiation insolation, changes. It's highest at what we call the subsolar point. The subsolar point is the latitude, for lack of a better description, of land during a specific day that is going to be directly under the sun. That's where there is no shadow. It's the sun would be directly overhead, 90 degrees straight up at noon. And the solar radiation falls off from there. It's basically the way the light is hitting a sphere. Okay, if the light source is here, then the light source coming in this way, then the light source is going to be where it's hitting the sphere perpendicular is at its strongest. But as the surface curves away, you're spreading that light out over a larger area. This helps to explain the seasons and the differences in climates as we move away from the equator on the Earth. Now, our subsolar point moves back and forth day to day across the Earth in a predictable pattern, going from 23.5 degrees south latitude to the equator to 23.5 degrees north latitude, back down to the equator, and then back down to 23.5 degrees south latitude. These are the solstices and the equinoxes. Whenever the subsolar point is at the equator, we call it the equinox because the day is equally, for everybody, 12 hours day, 12 hours night. When the subsolar point goes to the northern tropic of Cancer, it is summer in the northern hemisphere. And so you have areas where you go from 12 hours of daylight up to actually 24 hours of daylight in the northern hemisphere and down to 0 hours of daylight in the southern hemisphere because of the tilt of the Earth also. When it goes to the southern tropic, the Tropic of Capricorn, then it's reversed. It's winter in the north, summer in the south. So we have that energy that changes. Basically, that energy measurement at the equator on the equinox is 342 watts per square meter. And so as we go up in latitude, that will change during the course of the year. In my physical geology class or physical geography class, one of the things that we do is we find the amount of insolation during the course of the year at different points on the Earth and actually map that out. So you can graph it out so you can see how that changes. So part of this gets into also a property of the Earth called albedo. Albedo is a specific term that we use to mention how reflective a surface is. Now, it's reflective not in terms of mirror polish. So if you look at this ball, this surface here, you can see right here, looks mirrored, but if I turn it to where it's been more rubbed, you can see it doesn't shine as bright. The shininess of it isn't really what we're meaning by albedo. What we're meaning instead is more like the difference between, between the colors on this pen, okay? This is probably an easier way to do it. Yes, the shininess has something to do with it, but I want to make it a little more basic for you. So the albedo is how much light is reflecting off of the surface. White surfaces reflect almost all the light that hits them. Black surfaces reflect almost none of the light that hits them. So we can see how the albedo of the Earth changes over time. If an area is more reflective, it tends to be cooling. If the area is more dark, it tends to be more heating because it's able to absorb heat. So one of the things that we can talk about also, your book covers, is black body radiation, which goes over the curve of how we would expect the wavelengths of light that are being given off by a body at a specific temperature to look. It has a great illustration on page 511 of what a black body radiation curve should look like for the Earth and for the Sun and the wavelengths underneath it. We're not going to go into that. What we have on that page actually is this illustration here showing the energy coming in and how the energy interacts in the atmosphere and on the surface of the Earth. So we have light that comes in, it's reflected from the clouds. We have light that comes in, it gets down, and it goes down to different surfaces. And it shows you what the albedo of these different materials are. So in this term, they're giving it as a percent reflective. So clouds, 70-80% reflective. So 70-80% of the light that hits them, thick clouds, gets bounced back off. Fresh snow, 80-95%. Grass, 20-30%. Forest, depending on the forest, can be 10-20%. Asphalt, blacktop, 5-10%. Dry concrete, 17-20%. So forth and so on. That's not all of the interactions that happen. When the light comes in, the light can be transmitted through, interact with the ground, and we can go from there. The light can also be scattered in the atmosphere. It can be reflected off the atmosphere. We can get into a very long discussion about the different ways that light interacts just in the atmosphere alone. But what your book brings up next is the greenhouse effect. Now, the greenhouse effect is probably one of those things that's a great example, but a bad illustration in my mind. It's a great example in what the effect is, but it's a bad illustration because the effect isn't the same. The greenhouse effect is the idea that heat gets trapped. If you walk into a building that's made of a lot of glass, your car, for example, this time of year, it gets to be very, very hot in the car. And that's because the heat is trapped. One of the reasons it's trapped is light energy is able to pass through your windshield or through the glass in your car or in a greenhouse and interact with the surfaces in there. Now, some of that interaction is going to change the wavelength of light to a lower wavelength or a longer wavelength. Usually a longer wavelength because energy has been lost, so it turns into heat energy. That heat energy goes up and it hits the glass, and well, lo and behold, the glass is opaque to the heat energy. It's transparent to the visible light, but it's opaque to the heat. So it traps the heat within it and allows the heat to build up. Gases in the atmosphere can do a similar thing, but they're not really technically trapping the heat per se in terms of keeping it in. They're making the path of that heat leaving the Earth longer. So what do I mean by that? It's not like there's a dome over the Earth holding it in. You know, like the cup here holding the tea in. Instead, dry this out a little bit so I don't drip over everything. Let's assume that my tea diffuser is a greenhouse gas molecule. Okay? Just got to get it so it doesn't drip too much. All right, so this is a greenhouse gas molecule. Let's just go with it. Okay, yeah, I know. It looks like the Starship Enterprise without the nacelles. If heat energy is trying to leave the Earth through what we call radiative cooling, that's heat is trying to travel up through the atmosphere back out, okay? And it hits a greenhouse gas molecule. It gets absorbed by that molecule. Now, it's going to do something. It can sit there for a little bit of time, potentially, but it's going to be radiated back out. Here's the thing. It's not going to be radiated necessarily in the same direction it can be radiated in any of the directions around it. So 360 degrees horizontally, 360 degrees vertically. So you have almost an equal chance if that ray of energy, that photon, gets radiated back downwards towards the Earth, which is quote-unquote trapping the heat. It's delaying how long that heat takes to get out of the atmosphere, thereby causing the atmosphere to remain warmer. Now, there are a number of different factors that influence the climate. When I was a grad student at Brown University, I was helping out somebody trying to plot out for a computer-based climate lab all the different factors that impact the atmosphere. It gets very complicated very quickly, and I'll go over some of that as we go through it. But just in general, some of the big factors that come into play. We have the solar variability and the orbital changes that can happen. We know that the sun goes through phases of brighter and darker in certain cycles. We also know that the sun is slowly getting brighter over time. We also have the eccentricity of the Earth, and I'm going to refer you to page 513 in this because I'm not going to try to draw them out for you. But the eccentricity, we talked about this in chapter 12 on the glaciers, how the orbit of the Earth goes more circular to more elliptical and back over the course of what is that, about 400 to 100,000 years, basically, depending on the cycle. We have the obliquity of the orbit. That varies on a 41,000 year cycle, and the precession of the axis. The obliquity is how the axis moves back and forth between about 21.5 degrees to about 24 degrees, thereabouts. It goes back and forth like this over time, and then the precession is how the axis actually rotates around like this. So the same, you can imagine it's going back and forth like this as it's rotating around also. And those are, if you remember, are called the Milankovitch cycle, and that actually plays a role in it. The Earth's albedo plays a major role. I took a trip back in the early 2000s to Washington State to visit my aunt with my family back up there, and one of the places I wanted to go was Mount St. Helens. We went to Mount St. Helens. This is about this time of year, maybe early May, and one of the parking lots was still full of snow. They just scraped all the snow off the parking lots whenever it snowed, and they stored it in this one parking lot. When you walked out onto that parking lot, there was a dramatic drop in temperature. The temperature that day was probably in the order of 64, 65, 66 degrees, somewhere in that ballpark. You walked out onto the snow to cross over, to take a shortcut through the parking lots. The air temperature dropped 20, 30 degrees. I mean, it just dropped noticeably. It was a lot colder. And part of this is because that the snow is actually reflecting all that energy away from it. So one of the things that we see with glaciers actually is that glaciers that are fairly white and pristine do not melt anywhere near as fast as glaciers that are darker. Darker material on the glacier will cause the glacier to melt faster. Same thing with snowfields. So the albedo of the Earth, it can change things up. So the darker the Earth is, the more heat it's going to retain. The lighter the Earth is, the more heat it's going to reject. So things like cloud cover, plant cover, have an effect on the albedo of the Earth from a day-to-day basis. Some other things that can play a role in changing the climate, other than the greenhouse gases, are going to be things like the clouds and particles that are in the air. This is actually one of those interesting ones where you get into this feedback loop. Dust particles are needed to be in the air to provide points for nucleation, so that water will or water vapor will transform into water droplets. That can increase the amount of clouds. Well, if you do that enough, you get a cloud that's dense enough that it's going to cause rain. That rain decreases the amount of particulates in the air, therefore reducing the amount of ability for nucleation to occur, making it less likely clouds are going to form for that time period of time. So you get this whole cycle that can feed into itself as a limiting feedback loop. That's one of the interesting things, is that if you put more dust in the air, you can increase the amount of clouds, you'll increase the amount of rain for a short period of time, then the rain's going to wash all that dust out. You can see this when we have those quick sprinkles that occur during the beginning of the monsoon, where you get those large drops that come down, they make the splats on your car and on the sidewalk, but then dry up without raining, getting everything wet, and your car is really dusty wherever the raindrop fell. Let's see. Volcanoes also can play a role, as we've discussed back in the beginning of the semester, how the volcanoes have three primary eruption materials. They have the lava, they have the particulates, and they have the gases. And really it's the gases that play a major role in greenhouse gases, but it's mostly water vapor followed by carbon dioxide and sulfur dioxide. Sulfur dioxide can actually cool the planet down if it gets high enough up into the stratosphere to cause a haze, where it will then reflect a lot of the sunlight away. Water vapor is actually a greenhouse gas. It will help to trap heat or delay the heat. Carbon dioxide, the same thing. Plate tectonics plays a role, in part that in multiple ways. Plate tectonics can expose more rocks to weathering, and depending on the type of weathering that's happening, that weathering can have an effect on the atmospherics of the Earth itself, in the atmospheric chemistry of the Earth. The mountains can actually be shoved up high enough. The Himalayas are actually shoved up high enough that they actually divert the northern jet stream. Then you have the way the continents move around. They can change the ocean circulations, which changes the way heat is distributed throughout the planet, because the major engine distributing heat across the surface of the Earth are the ocean currents. So if we look at the Earth's climate through time, the Earth has had a number of different climates. We're not going to get into all of them, but suffice it to say we've had everything in terms that life in some way, shape, or form, as we know it, has seen everything from a snowball Earth, where the Earth was completely glaciated over, to almost a desert world during Pangea, during the height of Pangea at the Permian-Triassic boundary, where the world was basically had a very large desert covering it. It's been warmer, it's been colder, it's been all over the place. Nothing at this point, just for a clarification for you, nothing that is forecasted to potentially happen to the Earth anytime in the next 100 years, 1,000 years, 2,000 years, or even a million years is outside of the experiences of our species. So that's the good news. Our species has been through some of this has been through all of this already before. we adapted then. The question really becomes is, can we adapt now? Your book goes into a nice little talk about temperature over the last 45, 50 million years, like the early Eocene, where we had a brief thermal maximum, where temperature was much, much warmer than it is today, all the way down to what it has in the last million years, talking about how the Milankovitch cycle works, etc. The last few thousand years is where we start getting more interested. One of the things to keep in mind also is when we're looking back at the past climate, and this is a great example of it, page 520 in your book. Keep in mind, the further back in time we look, the less temporal resolution we have. Notice how on the scale here, we are in thousands of years before present, and then we get to millions of years before present here, and how that scale keeps getting smaller and smaller and smaller. And so each little increment on the graph is a larger increment of time. This is very prevalent in anything we're doing in geology, and we're looking back through the rock layers, especially the fossil record, is that our ability to resolve small increments of time disappears the further back we're looking. And so our estimation of what we're seeing kind of gets a bigger bracket around it. Doesn't make it any less viable or any less realistic on what we're seeing or what we've calculated. It just means that we kind of have a broader brush we're painting with in terms of looking at what the temporal range is. Not temperature range, but temporal, as in time. So in the modern world, we've seen temperature increasing about 3/4 of a degree centigrade from 1901 to 2012. We've seen the temperature increase in general. It's been more the last 60 years that it's been increasing than the initial 100. This is going to cause precipitational changes. Remember when we talked about glaciers, I asked the question on how do we form glaciers, because you can't form an ice age by simply cooling the planet. That is nonsensical from a thermodynamic standpoint, because you need a lot of precipitation in a fairly short period of time to create glaciers. Remember, it takes 50 meters of snow to start to make glacial ice. So in order to make a glacier, we need not only an area to be cold enough to retain snow year-round, we need a climate that is also at some point warm enough to pump a bunch of moisture into the atmosphere so we can have a lot of precipitation. So the warmer the atmosphere is, the more moisture it can hold. The colder the atmosphere is, the less moisture it can hold. So back to ice ages, the idea is that we have something where northern and southern hemispheres are getting colder in the extremes, but near the equatorial region they actually got warmer. Now, as things change, we're going to see other impacts. We're going to see sea level change. How much sea level will change? I have some problems with that, as we mentioned before, talking about glaciers. The amount of sea level change was anywhere between 200 and 400 feet previously. At the height of the last ice age, we have a lot less ice than that now. Yet there are some people out there claiming we'll see 400 plus feet of sea level change. I don't think so. I think we're probably lower than that. Doesn't mean we won't see sea level change in the order of 100 feet potentially. A lot goes into that, trying to make those calculations and what happens. You have to think about where the ice is, how the ice is interacting, how the ocean temperature changes, etc. And also, when we talk about sea level rise, remember we talked about isostasy. We have to understand what the local area is undergoing so we can back out that estimation in terms of what is the local tectonic situation, the local isostatic situation doing and how fast is it doing, to make sure that we're not including those calculations in, or those effects into our rise. Now, perhaps one of the most difficult areas on this is the climate models. We use a bunch of different models. Some of the models are the same ones that we use for the Earth. Now, I will give a criticism of those models. Some of those models have missed the mark already. We're almost 20 years on from when some of these first models were coming out, and we have not seen as much change as those models had predicted. In a couple of cases, we haven't seen anywhere near the minimum amount of change that were predicted. This doesn't make these models invalid. That just tells us that maybe the models are not taking in enough information or enough consideration of other factors that we have left out to simplify things. And that's one of the things that we have to keep in mind. Whenever we build a model of the Earth's climate, we are making an oversimplification of it. Now, a lot of people will take that to mean, oh, well, the models are no good because it's going to overestimate things. Well, that can also mean it can underestimate too. Now, the ideal model, the best model in the world, would be one that not only would predict the future, but would recreate the past. We don't have any models that recreate the past yet. We can give them the current data and they can't recreate the past. But our models are getting more accurate. Now, the problem with a lot of our models, our forecasting models, is the shorter the distance between now and the prediction, the better the models are. Look at your weather forecast. Today, weather forecaster tells you what's going to happen in about 3 days. They're pretty spot on at this point. When I was a kid, not so much. There could be a lot of variability. But they're getting better. Now, what are the effects of this going to have? The effects are going to be innumerable. You're going to have effects on the biosphere, on agriculture. We're seeing this already in some areas where the growing season in some areas is shortening because it's getting too hot. In other areas further north, the growing season is getting longer. You can make the argument, well, we just adapt and move where we're doing the growing. That helps to some degree, but that's only a temporary measure. One of the major ones that's concerning is ocean acidification. Ocean acidification, because carbon dioxide, when you mix with water, if you remember when we talked about sedimentary rocks and weathering processes, that creates carbonic acid. Carbonic acid is an acid. It's a weak acid, but it's still an acid. It makes it harder for corals and certain bivalves to grow because they can't put down their skeletons as easily. So we have that. We have the idea, again, the sea level rise and changes that are going to affect some areas. That can have an influence on storm events also in terms of hurricanes and typhoons. So what can we do to change this, to stop it? Well, on one side of it, not a lot, at least not a lot real quick. This is a problem that has been more than 100 years in development. You can't flip a switch and make it stop overnight. You cannot flip a switch and reverse it overnight. So this is going to be a problem that if you go too far the other way, you can make it worse in the wrong direction also. So this is one of those things where, yeah, we're trying to seek a balancing point, but we're trying to seek a balancing point in a dynamic system. So you got a wave going back and forth inside this while you're trying to balance it. It makes it much more difficult. But there are things we can do. We can try to manage solar radiation. Some people have done that by trying to change the amount of radiation being absorbed by the planet, seeding clouds so that there are more clouds to increase the amount of albedo of the Earth. Some people have talked about putting shades up in space to shade the Earth. There's trying to control carbon dioxide in the atmosphere. One of the The weird things about it, though, is that the increase in carbon dioxide has also come with a greening of the planet. So we're actually seeing more plants on the planet now than 20, 30 years ago. It's getting greener, in part because carbon dioxide is plant food. In fact, if you ever go to a greenhouse growing facility, they actually deliberately increase the amount of carbon dioxide in their growing facility to almost 3 times atmospheric levels in order to make the plants grow faster and produce more. We're not going to get rid of carbon dioxide from the atmosphere. That's been done before. We get a snowball Earth. Not a good idea. The Earth freezes over. But there are things that can be done, not just at the global level, but at the local level. Sure, you can change to LED lights. You can get solar put on your house. Unfortunately, all but one alternative form of energy don't fit the bill. Solar power is great, except at night. If you don't have a way to store the energy, so battery technology is going to become key. Batteries in and of themselves are a different story, including some of what the batteries are made out of is rare materials, not necessarily good stuff to work with from a environmental standpoint when you have the byproducts. So that has to be worked out. Wind power is great when the wind blows. The wind doesn't blow. Then you get into some interesting battery storage with wind power called a hydrodynamic battery. The idea is you have 2 dams at different heights, and you pump water from the low dam to the high dam when it's windy, and then you let the water run back out when it's not windy, so you have power in those lower times. There's ocean current power, which is being worked on, hydrothermal power, but no matter what, we're still going to have other power sources. Probably the one that we're really going to have to look into is going to be nuclear power. Now, a lot of people get scared of nuclear power because of the connotation of nuclear power plants such as Chernobyl or Fukushima, and as well as nuclear power in terms of nuclear weapons. But that's only one class of nuclear power plant. There are other classes, other designs that aren't as reactive. They don't produce as much bad waste. They can use their waste as fuel sources. So nuclear power should not be ruled out at all. In fact, actually, if you look at the average American's power usage over their average life, and let's just say for the sake of argument, that's 80 years. How much coal is needed to fuel that Americans' power needs? Well, probably something like 300 metric tons of coal. That's a lot of carbon dioxide. How much uranium, if we were to do a nuclear power plant? About 2.2, 2.5 kilograms, or 6 pounds. You do the math. We're talking the same amount of energy over 80 years. And again, depending on the type of reactor that we use, that changes what sort of byproducts we get. The reason we get byproducts from most nuclear reactors worldwide right now that are nasty, that last for tens of thousands of years, is because we use a form of nuclear reactor that is a reactor meant for breeding plutonium. Why plutonium? Well, we use plutonium for nuclear weapons. So if we got rid of our nuclear weapons, got rid of our need for plutonium, we could go to different systems that didn't generate plutonium, and that would be a more clean form of nuclear fuel. Beyond that, though, there are other things that can be done. We need to rethink the way we construct our cities. We need to rethink the way we construct our yards, or construct our homes. I was surprised about a year ago, and very close to a year ago right now, I went to Singapore with my brother. My youngest son was doing a semester overseas in Singapore studying engineering there. When we got there, the first day we were there, it rained. Most of the morning it rained. And it rained fairly hard, on the order of about an inch an hour. I was surprised at how little runoff there was. There wasn't much runoff in the streets. There was hardly any. there didn't seem to be much runoff anywhere. And this is because Singapore has done a outstanding job at using or holding on to their water. Fresh water is very precious there and is in short supply, given the way Singapore is a bunch of islands that have been infilled together to create a larger landmass. Some of what they've done is they mandate now new buildings have to have rooftop gardens. So those rooftop gardens also change the albedo of the city. You don't have exposed steel, glass, and concrete, which are going to absorb heat and hold on to that heat. Walk by a stucco house after sundown on the west side, you feel that heat radiating off of it because that house is a heat battery. Walk onto a street from a grassed yard, and you'll feel that change in the heat at night. So they've done things like that to do it. Now, we have a different climate here, but we can do similar things. We can do rooftop gardens of some sort to try to change the albedo. We can change the layout of our city so that we have less materials that are going to absorb heat in the sun as long. We can do more trees to try to provide shade for areas that we have to have it. Who knows, even the development of these self-driving cars may even play a role, because if you have a fleet of self-driving cars, nobody had a car in the city, and we're really talking a large city here, not a small city like Nogales, but something a million plus or several million people. If you had a fleet of self-driving cars, you don't need as much parking space. If nobody has a car in the city, you don't need as many parking spaces. That means you have as much less asphalt, much less concrete. You can have more open space, more parks that will help lower the heat island effect. Just in your own yard, you can change it by planting, or in your own property, planting trees. Don't use rock as a landscaping material, landscaping cover. Use something like bark or wood chips instead. Rock actually can make the outside of your house hotter and make your air conditioner work even more during the course of the summer. So basically, that's what I wanted to cover with chapter 21, the climate. The climate is changing. Yes, the climate has always changed from day one. This is not the same climate today as we had 300 years ago, or 3 million years ago, or 300 million years ago, 3 billion years ago. Keep in mind, the Earth's climate is a dynamic system. So reversing climate change comes with a caveat that you got to keep in mind that the climate is dynamic. The climate is not static, so we cannot ever put the climate back to what it was X number of years ago, because it's a dynamic system. We can try to approximate it and try to get close to it with what we have today, but the system will be slightly different because all the variables in it are different. So with that, I'll talk to you guys later. Have a good one.